All right. Good morning, students. How are we today? I trust that we are good and we are staying safe. This morning we are going to be looking at physics. Our first topic is physics is electric field. So we will look at electric field, types of electric field, and electric lines of force. Possibly we also look at electrical potential energy, electric current, and electrical resistance. So we have done this before in our previous class. A field, while I was describing a field the other time, I said the field is a region or space under the influence of forces. Can be electrical force, can be magnetic force, can be gravitational force. So in this sense, if you are asked what is an electric field, an electric field is a region or space where a charged body experiences what? An electric force. So where a charge experiences force, that space is referred to as what? An electric field. And how can a charge experience a force? A charge can only experience a force where there is maybe another charge within that space. So that charge, another charge, will now be having an influence on the other charge. That's where the force comes in. It's just like you're having magnets. You will not know the field of the magnet except you bring another magnet or magnetic material close to that field. I'm sure you understand what I'm saying. If you bring a magnetic material close to a magnet, you will notice that the magnetic material will be attracted to the magnet because it's within the field. So the same thing with charge. So that's why I said here the electric field is just a way of describing the action at a distance of one charge upon another. Such a field is another example of a force field and is represented with electric lines of force. So what this thing is trying to tell us is that electric fields are represented with what? Lines of force. Since force is a vector quantity, an electric force field has both magnitude and what? Direction. So we are trying to describe an electric field in this sense. One, electric field has lines of force and it's what? A vector quantity because it's a force. A force is a vector quantity. You know what a vector quantity is? Vector quantity are those quantities with both magnitude and direction. So because it's a force, it has magnitude, it will always have what? Direction. Are you getting me? Now when we say magnitude, magnitude means size. When we say direction, it's either going towards the north, towards the south, towards the east, towards the west. It does not parabolate or rigmarole or move without direction. I get you are following me. So that is that. And the direction of an electric field at any point is given by the direction of what? The force acting on a small positive charge placed at that point. So the direction of an electric field is determined by what? The charge. That's what this one is saying. So if, for example, the curved line such as Pn represent an electric force, then the tangent to the line at points such as A, B, C indicate the direction of the electric field at this point. The arrow indicates the direction of motion of a small positive charge placed at each such point, hence the distribution of the field line at such point. The diagram that I'm going to show us is going to elaborate on this point I just made. So these are the lines of force. Now we have two types of lines of force. We have uniform lines of force and we have variable. The one described in the former note is the one in the B section. You will notice that it's a curved line. That's a variable field. The uniform field is A and the variable field is what? B. So this line, this curved line is the one we are trying to describe. Now if you look at it very well, you notice that there is an arrow indicating the direction. That arrow is tangential to the curve. A tangent is a line that is close to what? A curve. as described in this diagram. So this line, this thing here is a tangent. This one is also a tangent. This is also what? A tangent. So they are tangential to the curve, and that is how you determine the direction at a particular point. The direction here is not the same. The direction here is not the same as the direction here. The direction here is almost tilting upward, while this one is horizontal. So note, if you want to get the direction of the curve feed like this, you draw a tangent close to the curve. The direction of the tangent determines the direction of the field at that point. So like I said, there are two types of feed. We have uniform feed, in which the feed line are uniformly straight or straight. Then we have variable feed, in which the feed line are curved, as in this example. So this one is straight, these ones are straight, while this one is what? Curved. So take note of them. Now, electric lines of force. Let's go into this proper. What are lines of force? We are going to be looking at lines of force, then properties of lines of force. Electric lines of force is an imaginary line drawn in an electric field in such a way that the direction at any point or the direction of the given target gives the direction of the electric field at such point, or the path which an isolated positive charge would follow if placed in the field. As we have electric fields or lines of force, we also have magnetic lines of force. You can only observe this one very clearly when we are dealing with the magnet. For example, I've done similar things using magnet. If you want to determine the lines of force of a magnet, all you simply do is to get a piece of paper, put some iron fillings on top of the paper, then bring a magnet close to it at the bottom. You will notice that those iron fillings will arrange themselves in a particular order. That is the magnetic lines of force of that magnet. That is how you determine it. So for an electric field, it also has lines of force, and in most cases the lines of force are something we cannot see. That's why they say they are imaginary lines drawn in an electric field in such a way that the direction at a point, at any point, or the direction of the tangent gives the direction of the electric field at such point. Or if you don't want this kind of definition, you can also define it as the path which an isolated positive charge would follow if placed if placed if placed in the field. The path which an isolated charge or positive charge would follow if placed in that field. That's the electric lines of force. So patterns of electric field. The field above is an isolated positive charge, is radially outward. Now we have different patterns of electric field. We have the one that a positive charge will give, we have the one that a negative charge will give, then we have the one that a combination of both positive and negative charge will give. Naturally, when you place a positive charge in a field, you will see the lines of force coming out of the field or the charge. Are you getting me? If you bring a negative charge in the field, the lines of force will be going towards the negative charge. Are you getting me? So that is the convention. Positive goes out, negative comes in, just like opposites, one opposite the other. Man, woman, that's the pattern. So this next diagram will describe that to us. So we have them now. The first charge, look at the first one around positive charge. You notice that the arrow is coming outside. That's a positive charge. If you look at the B part, that is a negative charge, the arrow is going inside. And if you place two similar charge, like two positive charge or two negative charge, you know there is a law in charge that say positive charge, two same charge or two similar charge repel each other. Are you getting me? So that's where you see this one around two like charge. This is what will happen. They will not come together because they are what? the same charge. Look at the diagram. This is what you see. This is what you see. Something like this. This is what you see when you bring two the same charge together. And when you bring two opposite charge together, you see this. So that's that. Now in a plate, parallel plate, if you bring positive and negative, you will see this uniformity. So this is what you see. Take note of this pattern I've just described. I can ask this in the exam. Name or describe with a diagram uh, two charge, two the same charge placed in a field with a diagram. I expect you to draw something like this. Expect you to draw something like this. Or I can say in a field, describe two opposite charge, how they will look like. This is exactly what you will draw for me, something like this. So take note of that. Now, properties of field or electric lines of force. This property are summarized below. Number one, lines of force starts only on a positive charge and end only on what? Negative charge. The number of field lines starting or ending is proportional to the magnitude of the charge. So the number of the charge or field or the lines that you see is proportional to what? The magnitude, that is capacity of the charge. If the charge is very big, meaning you are going to see many lines of force. That's what it means. If the charge is big, you see many lines of force. If the charge is small, you see few lines of force. That's what this first information is saying. Number two, lines of force do not cross each other. Lines, if you look at this ones, this diagram here, you notice that there is no way, you don't bring them together. Lines of force, they cannot meet. They don't cross each other. If they cross each other, it will change the direction of the field, the direction of the force. I think, and it will not make sense. So that's what this second information is saying. Line of force do not cross each other. If they did, it will mean that the electric field would point in a different direction as at the same point, which does not make sense. So that's that. Number two. And number three, in a uniform field, the lines of force are straight in a uniform field. Take note. The lines of force are straight, parallel, and uniformly placed. If you look at all these fields are all uniform field. You will notice the pattern, especially this one. This one is a uniform field, parallel. Lines of force are parallel. Then uniformly spaced. The space in all of them is the same. That's the meaning. Uniformly spaced. So that's for that. Then number four, lines of force indicate the direction of the electric field. I've done this in number one. The field points in the direction tangential to the lines of force at any point. Lines of force, that's number five. The lines of force are continuous in any region with free charges. The lines of force does not end. It continues with any free charges. The lines are drawn in such that the electric field is proportional to the number of lines crossing unit area perpendicular to the lines. The closer the lines are together, the stronger the electric field. Take note, that's another serious point. The closer the lines, for you to get closer lines, meaning the magnitude of the charge will be very big. And the magnitude of the charge is big, meaning the lines of force will be many. So if the lines of force is many, meaning the lines will be very close. So if it's closer, you mean you are going to have a strong field. That's what it's saying. So take note of that. In our next slide, we'll be looking at potential difference and electric current. Or electric current, and let's start with electric current and potential difference. Before we go into electric current, there's something we must know about, which is the charge. We sometimes observe during the dry season, if you are wearing any silk cloth, if you tend to remove it, you will notice some crackling sound. Are you getting me? So those sounds that you notice are actually charge vibrating. Are you getting me? That's charge. If you want to also observe charge on a dry weather, close your room. If you have long hair, close your room, be in front of a mirror, try to comb your hair in front of a mirror. You will see sparks. Those sparks are charge. So an electric charge can be at rest. Now those charge in your hair, they are at rest. They are not moving. They are not motile. They are at rest. When charges are at rest, we call them static charge or static electricity. They are not moving. Are you getting me? When charge begin to move, we call it electricity or electric charge or electric current. So if you, that is where the concept of current comes in. When we say current is what? The flowing or movement of what? Charge. Are you getting me? Are you getting what I'm saying now? So that is what a current. Electric current, as I defined here, is represented with the letter I, capital I. Is defined as the rate of flow of electric charge along a conductor. So when charge begin to move, we refer to it as what? Electric current. Are you getting what I'm saying? So that's that. A stream of moving charge or electrons constitutes an electric current. We can describe the flow of electric charge along a conductor, e.g., a metallic wire, by expressing it in terms of quantity of electric charge Q, which moves past each section of the conductor in a given time t. The quantity of charge is measured in coulomb and time in seconds. Hence, current I is given mathematically. Now, when we define electric current as the flow of charge, the flow is determined per what? Time. If you want to measure flow, you rate it per what? Time. So meaning we have two terms now to describe electric current. One is the quantity of charge that flow and the time it takes that quantity to flow. So if I'm going by this definition, mathematically, electric current can be represented with what? I, which is the symbol for electric current, is equal to quantity. Quantity of charge is represented with the letter Q over time. This next slide will explain better. So for current, you notice current is this letter I is equal to quantity Q over what? Quantity Q over time. So this is what? Electric current. Current is equal to quantity of charge over time, where the quantity of charge is in coulomb and time is in what? Seconds. So you can also describe an electric current or the unit of an electric current as what? Coulomb per seconds. And coulomb per second is referred to as what? 1 ampere. You go along what I have explained here, you notice that if Q is in coulomb and T is in time, the current I is in ampere because quantity over time is ampere. Hence, 1 ampere is 1 coulomb per second. That's what I just explained. And thus, we can define the coulomb as the quantity of electricity passing a section of a conductor in 1 second when the current is 1 ampere. The commonly used multiples of ampere are in the next slide. Let's see them. So these are the multiple or sub-multiples of ampere. Ampere is the unit of current. Take note. SI unit is ampere. You can have other units like coulomb per second, which I have described. So other sub-units, we have milliampere. Milliampere means 1,000 of an ampere. Then we have microampere. Microampere means 1,000,000 of an ampere. And the symbols are there. This is 1 milliamp, which is 1 over 1,000 amp or 10 raised to the power minus 3 amp. Then 1 microamp, which is 10 raised to the power 6 minus 6. These values, you will notice they are very low. So take note, they are very low. They are used in those small electronic device that doesn't consume much current. Mm. That's where they are used. Such low current are common in transistor radio, you see, electric calculator, you see, those are where you find the application. Now, what do we use in measuring current? What do we use in measuring current? I will describe it in the best possible way I can, but I'm going to give us a diagram when we identify this. We have seen them before, we are going to identify it. Now, ammeter is an instrument for measuring current. Milliammeter measures smaller current, like we have milliamp. Milliammeter measures small current. Very small current are detected by sensitive instrument called galvanometer. Take note, galvanometer is more like um, a neutral instrument. It can be used to measure current. It can also be used to measure potential difference. It depends on how you alter it. You connect a shunt to it, you know it will measure different things in different perspective. So that's what that. But now we are looking at ammeter. Ammeter is said to be sensitive if it can detect or measure very small current. That's how to know the sensitivity of an ammeter. It is said to be accurate if the current is measured is close to what the true value of the current flowing the instrument. Symbolically, is represented with this. Anytime you see something like this in an instrument, that is how you know an ammeter. That A represents ammeter. Are you getting me? A is for ampere, ammeter. So anytime you see any kind of this symbol in an instrument, you know that that instrument is what? An ammeter. So take note, I'll give us some diagram. We need to identify them based on my description. So that is for ammeter. Now we are going to be looking at the next one, which is electric potential difference. Electric potential difference. The potential difference between any 2 points in an electric field is defined as the work done in moving a positive charge of one coulomb from one point in the electric field to another. The unit of potential difference is the volt and is defined as follows. 2 points are at a potential of 1 volt if 1 joule of work is done per coulomb of electricity passing from one point to the other. Unit of potential difference, other unit of volt and 1 microvolt is just similar thing. Now I've defined electric potential as the work done in taking a charge. Now it is only when charge begins to move that you experience potential difference. Are you getting me? So the work done by that charge in moving from one point to another is referred to as what? Electric potential difference. So when charge is not moving, you cannot measure potential difference. It's only when they are moving. And when they move, they constitute electric current. So if you look at it, electric potential and electric current, they go pari passu. They go together. You cannot isolate one from another. Sometimes you say the current is low or the voltage is low. Are you getting me? You say the current is low, the voltage is low. I'm sure you can paint something, you can relate something with that. Now what it means is that you can only measure current where there is a potential difference. If there is no potential difference, you cannot measure current. Still also, it is only when there is current that you measure potential difference. So that's the concept there. So 1 microvolt is 1 over 1 million of what? Volts. 1 milli is 1 over 1000. 1 kilo is 1000 volts. Kilo is 1000. Instrument for measuring potential difference, you see it here. It's represented with a letter V. This is symbolically how it is. The instrument, if you look at the instrument, you see this letter V. That's how you know. So that's for that. Then the other one we have is electrical resistance or resistance. Resistance, resistance. From that word resistance, that is to tell you that you something that does not allow another thing, or it limits another thing. So resistance, or it opposes another thing. So the resistance in this sense is the opposition to the flow of what? Current or flow of charge. When a device opposes the flow of what? Charge, that device can be seen as what? A resistance. Virtually every device that we have has some level of resistance in them. It's only when the charge or the potential differences is able to overcome that resistance that the instrument will work. If it does not have enough current to overcome the resistance, you will not see enough effect of it. For example, you have a light bulb, sometimes the current will be low. You know why it is low? Because there is some amount of resistance there in the component of what? The bulb. So when you bring more current, you will notice the effect of what? The current in the device. If you bring small current, that current will not be enough to power it the way it ought to be, because you need to beat against so many things that is made up, the bulb is made up of, in order to give light. So that's what I'm trying to say. So resistance can be defined as the opposition to the flow of charge or current or electrons. Its unit is the ohms. The unit of resistance is ohms. It is stated here OHM, ohm. Any component that offers opposition to the flow of current in a circuit is called a resistor. The resistor is different from an insulator. Insulator can be any device that does not allow current to pass through them. A resistor allows current to pass through them, but it is in limited order. It does not just stop the flow of current. Are you getting me? Unlike an insulator can hinder the flow. That's why if you glove your hand with any insulating material, you can touch electricity without the electricity harming you. Are you getting me? So that's what I'm trying to say. It does not allow current. For an insulator, it does not allow current to pass through it. But for a resistor, it allows current to pass, but it's limiting the current to some extent. So take note of that. We have seen the different materials, conducting ability, and accordingly known. We have good conductors, insulator. In current electricity, we think in terms of ability of substance to resist the flow of electricity through it. A good conductor is therefore said to have a low resistance, and a poor conductor a high resistance. Very good insulator may be regarded as having infinite resistance, hence no current can pass through an ideal insulator. Silver offers the least resistance to the current, however it is too expensive for normal use, and so copper is generally used as conducting wire and cable in electric circuit. When a high resistance is required in a circuit, Constantine, magnum and nichrome wire are used. It is represented with the letter. Take note of the symbol that we use in representing resistance. Either you have this or you have this. So these are the symbols that we use to represent electrical resistance. Now in an electrical resistance, we have different type of resistor. We have, that is in the lab, we have different type of resistor. We have a rheostat. A rheostat is a variable resistor. We have a resistor bus. A resistor bus has key on it head. Then we have those standard resistor. A standard resistor is a resistor in which the resistance is known. You may see it, you may see 2 ohm, 3 ohm on top of it or labeled across it. That's how you know a standard resistor. They are very small, they are cylindrical in shape, they are small, they are always written the value of the resistor across it. So take note of that. I will show us pictures of this device, ammeter, voltmeter and resistor. Then we identify them and submit. I hope this is clear. If you have any question based on what I have explained, you can relate it to me via our platform. Thank you very much for listening. Please stay safe. God bless you.